Introduction of half-life and rate of decay. A macroscopic sample of any radioactive isotope consists of a vast number of radioactive nits. These nuclei do not decay at one time, but decay one by one over a period of time. So this is the basic formula for the half-life and rate of decay. The number of decays that occur in a very short time is then proportional to time and to the total number of radioactive nuclei. As we can see from the equation below, the number of decays equal to lambda times the number of decays times time. The minus sign means the number of decays is decreasing. So we rewrite new equation like that, which is rate of decay times lambda over times. So it is equal to negative lambda times number of decays. Lambda is a measurable constant called the decay constant. The greater lambda is, the greater the rate of decay, more radioactive that isotope.
Radioactive nuclei decay one by one, so the number of parent nuclei is decreasing. From the sample of A, the nucleus emits an electron and it will become like the picture in B. The proton number will become 7 and another decays happen in C. This symbol is for the number of decays that occur in the time of interval.
So for the exponential decay is a process in which a quantity decreases over time in a manner proportional to its current value. So this mathematical concept is often applied in physics to describe various phenomena where a quantity diminishes at a rate proportional to its current size, which the general formula is shown below, where you can see n times t is the quantity at time, and n0 is the initial quantity where time is equal to 0, and k is the decay constant, which is a positive constant, and e is the base of the natural logarithm. Following with the two figures a and b, a the quantity n representing the parent nuclei within a specified 1C sample exhibits exponential decay. In this context, we consider a sample initially containing number of 1 times 10 to the power of 22 nuclei, whereas in figure B, the rate of radioactive decay as well as the number of decays per second also follow an exponential decrease. And the half-life of 1C is 5,730 years, indicating both the parent nuclei count n and the decay rate, which is the difference of nuclei divided by the difference of time, reduced by half every 5,730 years. So for the decay rate, R, representing the number of decays per second, is synonymous with the absolute value of the change in the number of parent nuclei, which is the difference of the nuclei dividing by the difference of time, and is referred to as the activity of the sample, the absolute value denoted by vertical lines in a convention to express the positive magnitude of a quantity, and the absolute value of the difference of nuclei dividing by the difference of time is written, and it's directionally proportional to the quantity n. Consequently, it also undergoes exponential decrease over time at the same rate, the activity of pure sample at a given time as well.
Half-life. Half-life is defined as the time it takes for half the original amount of parent isotope in a given sample to decay. The longer the half-life of an isotope, the more slowly it decays and hence is smaller. Conversely, very active isotopes have very short half-life. The precious relationship between half-life and decay constant. For example, half-life of carbon is about 5,730 years. Let's say 1.00 times 10 power of 22. After 5,730 years later, it will contain 0.5 times 10 power of 22. After the 5,730 years, it will contain 0.25 times of 10 power of 22. From 1.00 times 10 of 22, we just divide by 2 to get the half-life after 5,730 years. Okay. For the formula of half-life, half-life is equal to ln 2 over lambda. Ln 2 is equal to 0.693. So we can use 0.693 over lambda.
So we will jump into the deriving the half-life formula. So as we know, half-life formula is ln 2 over lambda or equal to 0.693 over lambda. We will start derive from radioactive decay law, which is the formula is n equal to n naught exponential to the power of negative lambda t. So we will start deriving by setting times equal to half time formula and n equal to n naught over 2 due to the half time formula. When we derive to the formula n equal to n naught exponential or the power of negative lambda over lambda t, when we derive it, we will get n naught over 2 equal to n naught exponential the power of negative lambda half time. So we will continue the calculation, and 1 over 2 we brought to the front equal to exponential the power of negative lambda half time. So at the end we will get exponential the power of lambda half time equal to 2. Then after we get the answer from the derived into the formula, we will natural log both sides, which is we will put ln both sides. So ln and exponential will be out, and it will be lambda half time equal to ln 2. So we rearrange the lambda will go to the other side. So the answer will be half time equal to ln 2 over lambda, which is equal to 0.693 over lambda, which is it's same as the half time formula, which is it is proven. So the mean life of an isotope can be quoted as mean life equals to 1 over lambda. So the radioactive decay law equation can, the power of negative lambda time, the lambda can be substituted by the mean life equation, which is it will become power of negative time over mean life. And the other equation of radioactive decay law, also the lambda can be substituted by the mean life, so it will become power of negative time over mean life.